In this video we have a look at how we determine some of the exact values that we use in trigonometry. Let's first of all though have a look at an example where we want to determine an unknown side x in a right-angled triangle. To find the unknown side we're going to use the trigonometric ratio sine. That's because we have the side opposite 60 degrees and we also have the hypotenuse. So we'll write sine of 60 degrees as the fraction x over 12 or opposite over hypotenuse. We can then multiply the 12 across and then use our calculator to determine the approximate solution for x as 10.39 centimeters. You'll notice that we've referred to this as an approximate solution, that's with the two squiggly lines next to x. But we can sometimes in trigonometry find an exact solution, and that can be very useful if we're doing a problem that involves a series of steps to give us the most accurate answer at the end of our solution. Let's have a look at how we determine some of these exact values for some common angles in trigonometry. We'll first of all consider an equilateral triangle. Each of the sides has a length of 2 units, and that's arbitrary. We're just doing that to help us with this particular problem. What we'll do is we'll put a bisector in our triangle, and it's a perpendicular bisector because of the symmetry of this equilateral triangle. So at the base of the triangle, each of the lengths are 1 when we split it up into 2 parts. We'll label the height of the triangle h. So basically what we've done is created a right-angled triangle on the right-hand side of our diagram. Now to determine the value of h we'll use Pythagoras, and that's going to be the square of the hypotenuse minus the square of the smaller known side, which is 1 unit. When we go through and solve for h we get a value of root 3. We also know that because it's an equilateral triangle, each of the angles at the vertices is 60 degrees, and because we split our triangle in two, the angle that's at A on the right hand side is 30 degrees. Let's now remove our working and have a look at that right hand side triangle that we created in isolation. What we'll do is we'll have a look at the sine of 30 degrees. Now we know that sine is opposite over hypotenuse, so in this diagram the side opposite 30 degrees is 1 and the hypotenuse is 2, so we get a half. If we then consider sine of 60 degrees, we know the side opposite the 60 degree angle is root 3 and the hypotenuse is 2, so sine of 60 degrees is root 3 on 2. A good idea now would be for you to go through and find cosine and tan of 30 degrees and 60 degrees and compare it to the table which you'll see towards the end of this video. Now let's have a look at an isosceles triangle with sides of 1 on the shortest sides. Now we'll first of all determine the hypotenuse h, and we'll use Pythagoras there, so it's 1 squared plus 1 squared. That gives us a total of 2, and then the value of h is root 2. We also know that because it's an isosceles triangle there are two congruent sides, and those sides are DE and EF. And with those sides being the same, the angles opposite them are the same as well, and they add up to 90 degrees because there's a right angle at E. So both of those angles are 45 degrees. It would be a good idea to pause here and see if you agree with the upcoming exact values for sine of 45 degrees and cosine of 45 degrees. So based on opposite over hypotenuse, the sine of 45 degrees is 1 over root 2. Given the nature of the isosceles triangle, it's also easy to see that cosine 45 degrees is equal to 1 on root 2. We're now going to have a look at the exact trigonometric values based on the triangles that we've just seen. We've also included 0 degrees and 90 degrees, which you may need to refer to on your calculator if you haven't done them before in a unit circle. So it might be wise to pause here, see if you can determine the exact solutions, and then check them in the video in the seconds that follow. So here are the exact values first of all for sine, then for cosine, and then for tan. Notice that tangent of 90 degrees is described as undefined. Now if you've seen a unit circle you probably would have seen why that's the case, but we can also define tangent as sine divided by cosine for any particular angle, and in the case of tangent of 90 degrees, if the denominator is cosine 90 or dividing by cosine 90, that means we're dividing by 0, so the tangent of 90 degrees is undefined. Let's have a look at how we now can apply exact values in the unit circle. Let's first of all consider sine of 240 degrees. The first thing we need to do is identify the location of the 240 degrees. We then need to determine the angle to the horizontal. So we can see that the angle between the given diagram of the angle 240 degrees and the horizontal x-axis has a gap of 60 degrees. We then need to ask yourself, in this quadrant, is sine positive or negative? And we know from the dashed line that it goes across to the vertical axis for sine, and that's on the negative part of the vertical axis. We also know that sine's negative in the third quadrant. So the sine of 240 degrees has a value similar to sine 60 degrees, except it's negative. So the sine of 240 degrees is negative root 3 on 2. If we're considering cosine of 330 degrees, we first of all draw the angle, determine the gap to the horizontal axis, identify that that's in the fourth quadrant, or looking at the dashed line we can see that for cosine measuring on the horizontal axis it's going to be a positive value. The value will be similar to 30 degrees, and in fact in this case, because it's also positive, it's exactly the same as cosine 30 degrees. So the cosine of 330 degrees is root 3 on 2.